Today we have a physics problem regarding an oscillating spring, horizontal oscillating spring. And it reads, a 200-gram mass attached to a horizontal spring oscillates at a frequency of 2 hertz. At 1 instant, the mass is at x equals 5 centimeters and has a speed at 1 point Vx as negative 30 centimeters per second. Determine A, the period, B, the amplitude, C, the max speed, total energy for part D. So, not everything's straightforward, well, except part A. And as you are no doubt aware, that, let me get my pen set up here, that the period T equals 1 over the frequency, and that is 2.0 hertz. That one's easy, and that's just simply 1/2, as you can see here, which we'll just say 0.5, and this is, of course, the units is seconds, and I'll just write sec so that the S doesn't look like a 5. So this is part A. Then work on part B, and it's the amplitude. Now, you could say, well, here's a displacement of 5 centimeters. Well, the problem with that is we don't know if that's the max displacement, thus the amplitude, so we have to figure out through some math. This was fun. Okay, so let's write a B down here, and we'll go ahead. And the way of figuring this one out is we could use the mechanical energy, and this will also help with part D, equals the kinetic energy plus the potential energy. And since this is a horizontal spring, the potential energy will be the elastic potential energy, not the gravitational potential energy. So, to get this one here, go ahead and put a little arrow. And this is where we're going to grab the amplitude from. This is 1/2 K, which is the spring constant, multiplied by the amplitude, squared, equals the kinetic energy. Again, we have a 1/2. And this is mass and velocity squared. And then this is plus the elastic potential energy, which is 1/2. And again, we have the spring constant here. And then x is a displacement. Okay, let's go ahead and plug in these numbers then. First off, the halves could cancel. I'm still on the race here. Since there's half, 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 that'll make things a little easier. But first, before we start plugging these numbers, let's get this spring constant here. So first formula we should use, or formula we can use, I should say, is this one. Okay, since we have the mass, could place the mass there. And remember that this is 2 pi frequency. The omega, that's the radians. So let's go ahead and square both sides since we're trying to going to get rid of this square root symbol here. But I am going to do this before we square 2 course, we know the frequency is 2, and this equals, go ahead and we'll this, and then the mass is 0.2 kilograms, since 200 grams divided by 1,000 to get it into kilograms. And let's go ahead and square both sides like I said we were going to do. And this gets rid of the square root. Go ahead and do this. So now we have 4 pi 4 equals k. That's a horrible k over 0.2. So let's multiply both sides by 0.2 to get rid of this. Put this over here. So we cross that out. So we have 0.2 times 4 times, oh, don't forget this, being that we squared this. Square the pi and 4. And this will equal the spring constant. So go ahead and plug that into your calculator. K will equal 31.58, but we'll just say 0.6. And this will be Newton meters for spring constant. So 31.6 times the amplitude, it's what we're trying to solve for. And the mass, again, we have it as 0.2 kilograms. And times, let's put some parentheses here. And this is times the velocity, and this is plus. And then K, the spring constant, 31.6. And then we're going to use the displacement of 5 centimeters, and that's going to be 0.05 meters, like this here, and then we're going to square that as well. So let's go ahead and bring this down, and this will be 31.6 a squared. Equals 0.018 plus, and then there's the second part, and that gives you an answer. Second part is 0.07 and 9. You add these two together, and you should get 0.097, and this is going to equal 31.6, and then we have the a squared. Let's divide out the 31.6, and then we're going to get a very minute number. A squared equals 0.0030696. Then we're going to square root both. And then we're going to get A equals 0.055, since we're using meters and kilograms. This is be meters. And then, of course, this will be 5.5 centimeters. So this part right here is your answer to part B. That's the amplitude. So I went ahead and erased all the work in this area, and I wrote the part B right here, 5.5 centimeters, 0.055. meters. Let's work on part C, which is the max speed. Now that we have the amplitude and the frequency and the period, we could easily find the max speed. So the number we're going to use, or equation, sorry, that we're going to use is W times A equals V max. So that is just 2 pi times the frequency, which is 2. We're going to multiply that by the amplitude, and we're going to use the meters. 55. And let's go ahead and multiply that together, and you will come up with 0.691 meters per second, or 69 centimeters per second. Another way we could figure that out is by the equation. So I'm going to go ahead and do this. And the spring constant was 31.6. And this is over the mass of 0.2 kilograms. And this is multiplied by 0.055. And you will get the same number. .69, and that's meters per second. So the answer to C is 0.69 meters per second, or 69 centimeters per second. Okay, and then part D for total energy. Again, the equation for total energy is ME. Well, that's the, here it is, 1/2 K spring constant times the amplitude. And this will give your answer in joules. So go ahead and calculate this. 31.6 times 0.055, and remember to square that. So multiply these together, and you will get 0.055, and this is joules. Now you could also do this if you wanted to go the long route, and you go ahead and plug in the numbers for this, and you'll get the same thing. But if you wanted to make it a little easier, just go ahead and use this, the 1/2 spring constant times the amplitude. And this is part D.